Have you ever thought that certain situations require more attention than others? Can a machine, like a person, adapt to the intricacy of the problem? Consider a computer program that works harder on challenging issues and changes its whole approach depending on the task's complexity. This is AdaTape, not science fiction. Last week, Google Research presented AdaTape, an innovative AI technique with transformer-based architecture that uses adaptive computing in a blog post. AdaTape uses its adaptive function to provide an elastic input sequence that may modify its computing budget. AdaTape, according to the study report, directly injects adaptivity into the input sequence rather than the model depth. It also employs a method for adaptive tape reading. This is done to identify which tape tokens are appended to each input based on its complexity. In the paper, Adaptive Computation with Elastic Input Sequence, they offer AdaTape. AdaTape employs an adaptive tape reading system to decide the number of tape tokens added to each input based on complexity. AdaTape is fairly easy to develop, has an effective knob for increasing accuracy when needed, and is also considerably more efficient than other adaptive baselines, since it injects adaptivity directly into the input sequence rather than the model data. AdaTape outperforms tasks like image classification and algorithmic problems, while preserving a favorable quality-cost trade-off. Let's start with standard neural networks. These are technological instruments that learn from data. Recognizing images, comprehending language, and producing speech are all commonplace. But do they realize that not all tasks are created equal? They tend to apply the same effort to all jobs, regardless of their difficulty. But aren't all visuals equally clear and not all texts equally understandable? Ideally, we'd like our tools to match their effort to the complexity of a task, much like a conscientious human worker. Here comes adaptive computation. Adaptive computation refers to a machine learning system's capacity to adapt its behavior in response to environmental changes. While traditional neural networks have a fixed function and computation capacity, i.e., they spend the same number of flops on different inputs, an adaptive and dynamic computation model modulates the computational budget it dedicates to processing each input based on the input's complexity. It simply involves a machine learning system modifying its operating method in response to the obstacles it faces. Why is it such a game changer, you might ask? There are two reasons why adaptive computing in neural networks is desirable. For one thing, they give an inductive bias that allows a variable number of computing steps from different inputs, which can be critical in solving arithmetic problems that require modeling hierarchies of varying depths. Second, it makes it easier to modify the cost of inference due to the increased flexibility provided by dynamic computing, since these models may be changed to spend more flops processing a new input. Inductive bias. This introduces a new degree of intelligence into computers, allowing them to process tasks differently depending on the underlying needs of the input. Consider it like instructing a machine when to race and when to walk. Inference tuning cost. It enables practitioners to manage the computer power allocated to processing fresh information, making systems more efficient. Today's adaptive models aren't ideal. Some employ conditional computing, activating a subset of parameters dependent on the input. This may be difficult to implement and wasteful. Others employ dynamic depth, which involves altering the number of layers or iterations used for each input, which can cause training and inference instability. As a result, Google researchers have developed AdaTape, a novel paradigm that employs adaptive processing. AdaTape is a transformer-based design that creates an elastic input sequence using a dynamic collection of tokens. AdaTape takes advantage of the adaptable feature. It also employs a vector representation to represent each input to dynamically pick a variable-sized sequence of tape tokens. According to the Google research team, AdaTape constructs a tape blank to hold all candidate tokens. AdaTape introduces the concept of tokens, the basic units it processes. Input tokens. These represent fundamental data like words or pixels. Tape tokens. These are selected from a set of choices called the tape bank. AdaTape employs a tape bank to store all candidate tape tokens that interact with the model via the adaptive tape reading mechanism to generate a variable length sequence of tape tokens. The researchers created the tape bank using two methods: an input-driven bank, which extracts a bank of tokens from the input while using a different approach than the normal model tokenizer for mapping the raw input to a sequence of input tokens, and a learnable bank, which is a more general method for generating the tape bank by using a set of trainable vectors as tape tokens. The tape tokens are then added to the original input and transferred to the transformer. The two feed-forward networks are then employed. The first is for original input, while the second is for all tape tokens. The researchers found that employing distinct feed-forward networks for input and tape tokens resulted in marginally higher quality. The researchers put AdaTape to the test over a wide range of parameters. They discovered that it outperforms all baselines that incorporate reoccurrence into their input selection process, offering an inductive bias that allows for the implicit maintenance of a counter, which is unachievable in traditional transformers. They also put AdaTape through picture classification challenges. AdaTape was tested on ImageNet 1K during the test. They discovered that AdaTape outperforms the alternative adaptive transformer baselines regarding quality-cost trade-off. AdaTape is more than just a theoretical wonder. It has demonstrated its worth in real-world applications. Image classification. It achieves 83.8% top 1 accuracy on the ImageNet 1K dataset, with only 86M parameters and 4.5B flops. This is far more efficient than other models such as VIT and DIT. Algorithmic tasks. AdaTape excels at jobs like complicated arithmetic problems, delivering near-perfect accuracy with fewer computational resources. Google AdaTape outperforms several adaptive baseline models regarding efficiency measures such as flops per sample and latency per sample. On ImageNet 1K, for example, AdaTape's efficiency outperforms models like PonderNet. AdaTape may be customized to match a variety of circumstances and requirements, operating as a chameleon that adapts to the task at hand. It is not only about developing intelligent systems, but also about developing systems that comprehend the nuances of intelligence. In addition to its performance on the Parity Challenge and ImageNet 1K, we assessed AdaTape's token selection behavior with an input-driven bank on the JFT300M validation set. They used heat maps to visualize the token selection outcomes on the input-driven bank to better understand the model's behavior. Lighter colors indicate that position is more commonly picked. The heat maps show that AdaTape prefers the middle regions more frequently. This is consistent with our past understanding, as central patches are often more informative, particularly in the case of datasets including natural photographs where the primary image is in the center of the image. This result demonstrates AdaTape's intelligence, since it can efficiently find and prioritize more informative patches to increase performance. Google concluded that the adaptive tape reading technique generates elastic sequence lengths on AdaTape. This also includes a new inductive bias, allowing AdaTape to tackle problems that are difficult for both regular and existing adaptive transformers. That's all there is to it. Google AdaTape is a potentially game-changing leap forward in the realm of adaptive computing, altering how machines engage with different complexities of tasks in a manner similar to how people adapt and respond. If you like this video, please like it, subscribe for more thought-provoking AI stuff, and don't forget to share it with your friends.